All right, let's get into this. We usually think of AI learning by just, grinding through mountains of data, getting a tiny bit smarter with every million examples. But what if an AI could learn more like an architect, starting with a totally blank page and then building a perfect blueprint of its world from the ground up?
And that's really the big question behind this fascinating new way of thinking about AI. We're not talking about just tweaking a model that already exists. This is true de novo learning, learning from scratch. So how on earth does a machine achieve total mastery when it starts with zero knowledge of the rules, the goals, or even what it means to fail?
So here's the core difference, and it's a huge one. On the left, you've got the standard way of doing things, reinforcement learning. It's basically a mouse in a maze, right? It just bumps into walls over and over and over again, slowly figuring out the path to the cheese through endless trial and error. But on the right, well, that's a completely different philosophy. This is an AI that doesn't just run the maze. First, it builds a perfect internal map of the entire thing. It becomes an architect of its own little world before it even decides to take a single step.
And this shift in thinking, it takes us way beyond just simple trial and error. It is a fundamental change in how an AI can perceive and interact with its environment. What's really cool about this is how it visualizes the two strategies. Most machine learning we see today, it's what you'd call a top-down approach. You start with this gigantic, overly complicated neural network, and you basically just prune it down. You snip away connections until it kind of fits the problem. But this new research, it flips that whole idea on its head. It's bottom-up. You literally start with nothing, and you grow the model, only adding the absolute essential pieces needed to build a perfect, lean, and super efficient map of the world. The big theory driving all of this is something called active inference. And honestly, it's a bit of a mind bender. It proposes that the main goal for an intelligent system isn't really to get rewards, it's to minimize surprise. Think about that. The AI builds this internal model of how it thinks the world works, and then its primary goal is to act in ways that prove its model is correct. It's literally trying to make its own predictions come true.
So, this core idea, it gives us a completely different kind of AI agent. It's not chasing rewards anymore. It's trying to avoid surprises.
And you don't have to take my word for it. The researchers themselves put it perfectly. The goal isn't just to maximize reward. It is to maximize the evidence for a generative model. Okay, so in plain English, what that means is the AI wants to prove that its internal blueprint, its map of what winning looks like, is the right one. The reward isn't the goal itself, it's just the evidence that the map is accurate. And this whole architect mindset, it even changes the way the AI thinks about rewards and punishments. A reward isn't just a number to rack up. It's a key destination on the map that you want to be able to get to. But a punishment, that's way more serious. It's not just a negative score, it's a hard rule. It's a solid wall on your map, a law that says you never, ever go here. It actually shapes the very structure of the blueprint itself.
Okay, so if this AI is an architect, how does it actually draw this blueprint for winning a game? Well, let's take a look at the three-phase process it uses to build it. It all kicks off with Phase 1, surveying the land. Here, the AI just messes around, acting randomly. It's not trying to win, it's just exploring, getting a feel for the physics and the basic rules of its world. Then comes the really cool part, Phase 2, designing the safe routes. This is where it starts to build its map. It looks at a few examples of success and starts connecting the dots, but, and this is key, it only keeps the pathways that form perfect, efficient routes between all the winning states. And finally, Phase 3, living in the city. The master blueprint is done. Now it just uses that map to play perfectly every time, and it can even update the map if it finds a new, even better shortcut later on.
Now, that master blueprint from Phase 2, it's got a pretty technical name, but it's really important. It's called a pullback attractor. I know, it sounds super complex, but stick with me, because the idea behind it is actually incredibly elegant. And this visual just nails it. A pullback attractor isn't just one path to a goal. You should think of it like a super highway of success. The AI finds all the different states that lead to a win, and it builds this dense, closed-loop network that connects every single one of them. Any point on this superhighway can easily get to any other point. It's a complete, self-contained model of what it means to win, forever.
So, all this theory sounds amazing, right? But does it actually work? Well, the researchers put it to the test to see if this little architect AI could really go from just fumbling around randomly to achieving absolute, total mastery.
So they built a custom arcade game that was specifically designed to be tricky. You had moving targets, bombs you had to avoid, and the rewards were really sparse, meaning they were hard to come by. It was a real challenge, especially for a traditional trial-and-error AI. So for Phase 1, the surveying part, the agent played randomly for 10,000 frames. Again, not trying to win at all, just gathering raw data, trying to understand the physics of its world, sketching out that first rough draft of its map.
Okay, so then came Phase 2, designing that perfect blueprint. How many winning examples did it need to see to build its entire superhighway of success? Get this. It only needed about 170 games where it got at least one reward. From just that handful of wins, it built the whole thing.
And now for the payoff, the real kicker. Once that blueprint was built, once it knew how to win, how many mistakes did it make? How many times did it lose? The answer is 0, not a single loss. Perfect play right from the very first game. And here's the data to prove it. This chart shows its performance in that final living in the city phase. Look at the top graph. The line for rewards, it just shoots straight up and stays completely maxed out at 11, the highest score possible. Now look at the bottom graph. The line for losses, it is dead flat, right at 0. Game after game after game. Just consistent, flawless performance.
So perfect gameplay in an arcade game is one thing. That's really cool. But this method, it represents something so much bigger. Why does this whole architect approach have the potential to completely change AI as we know it?
It really comes down to what we can call the architect advantage. First, it's unbelievably sample efficient. It learns smarter, not harder. It doesn't need to fail a million times to figure out how to win. Second, it's way more robust. Because it has a real model of the world's rules, it's not just blindly chasing a reward signal that could be easily tricked. Third, it is the exact opposite of brute force. That final model for expert play used only about 0.4% of all possible moves in the game. That's incredible efficiency. And finally, and this might be the most important point of all, this is a real step towards an AI that genuinely seems to understand its environment instead of just reacting to it.
The paper offers this just fantastic analogy to sum the whole thing up. Attractor learning would be like learning to ride a bike without learning all the ways to fall over. I mean, think about that. Instead of learning from a million painful mistakes, this AI just builds a perfect theory of what success looks like, and then it simply executes that theory flawlessly.
So look, this research isn't just about video games. It really points to a whole new way of thinking about machine learning, one where these agents build their own understanding of reality, right from first principles. And that leaves us with a pretty profound final thought to chew on. If an AI learns by building a perfect model of its world, what kind of world will it choose to build?